Hello and welcome to this set of lectures on chemical process modeling and simulation. Till lecture number 18, that set of lectures considered models of a flowing fluid from the perspective of a continuum, and then through those lectures we derived the basic conservation equations for overall mass, species, and momentum. Now we turn our attention to modeling energy of systems, and in order to model the energy of systems we are going to, before coming back to that framework of conservation equations, take a detour. We are going to discuss the fundamentals of thermodynamics in a set of lectures. You may wonder why we need to do this. In addition to, of course, presenting the fundamentals of thermodynamics and developing at the end of those lectures a model of a fluid at rest. Thermodynamics deals with rest states of a system, which we will see shortly, right? In addition to doing that, we will along the way acquire some important pieces that we will use in developing the equation for conservation of energy. This is going to be a fairly extended detour, but I believe that there is sufficient value added in undertaking this detour that I make bold to embark on this. We start from the very basics of thermodynamics by defining system, surroundings, and boundaries. System is an entity that is distinct from its surroundings, and the distinction is given by well-defined boundaries. Now consider this system arbitrary geometry. It is just shown as if it is a rectangle for convenience. That's it. This system has a boundary that separates the system from the surroundings. That is the system surroundings boundary. The surroundings spread out and ultimately eventually has a boundary which is isolating in nature. We will see what this means in a short while. And the system, for our convenience again, to facilitate generalization of studies various types of systems, we consider as if this system is partitioned into two, subsystem 1 and subsystem 2, and therefore there is a boundary that separates these two subsystems, and this boundary is internal to the system, and therefore this is an internal system boundary. Now what we observe is that the nature of the system surroundings boundary, this boundary, right, nature of the system surroundings boundary defines the nature of interactions or exchange between the system and the surroundings. So we will spend some time defining the different types of boundaries, which will essentially determine the nature of interactions that exist between system and surroundings. And in all of these interactions, we are ultimately interested in energy of the system, and how that energy of the system is exchanged with the surroundings. Nature of the internal system boundary, of course, therefore, by going by the same logic, defines the nature of interaction or exchange between the two subsystems inside the system. Finally, what is this isolating boundary? The isolating boundary of the surroundings isolates the system plus surroundings, which is all the content within this double blue border, right? So this boundary, isolating boundary, isolates the system plus surroundings from any interactions with the rest of the universe. Therefore, for our purposes, the entire universe may be confined to this, and our analysis may be confined to the system, the surroundings, and their interactions. Now I can make this brown boundary that is seen here, full line, which is the system surroundings boundary, also isolating, in which case there is no interaction between system and surroundings. There is only interaction between the subsystems, and I can call this to be system and this to be surroundings, or vice versa. So this sort of picture allows for different levels of generalization, and that's why this setup is drawn. Please do not take this kind of a picture literally. We must be able to visualize various engineering interactions, in terms of this kind of a paradigm, this sort of a paradigm. Now, we have to model the system surroundings and their interactions. These interactions and the systems and the surroundings may be modeled at molecular scales, microscopic scales, or macroscopic length scales. One thing I want to emphasize in thermodynamics, which is somewhat different from what we see in transport, is that this microscopic and molecular length scales are somewhat in textbooks. There are they are both conflated, and the same term microscopic seems to appear. And then there is also, of course, a mesoscale that is defined, which we will not get into at this point. We've been sort of talking about these three length scales: molecular length scales, microscopic length scales, and macroscopic length scales, which we sort of defined using Knudsen number, and we stick to that. So this, of course, macroscopic versus microscopic versus molecular. The key thing to understand is that we are going to develop some sort of a thermodynamic framework which is independent of the specific model scales and the specific nature of the model itself of the system and the surroundings. So this sort of sets us up on some path. So first we are going to spend time putting together some thermodynamic framework which is independent of these scales. All right, and the framework works at all scales, so to speak, and we will develop various relationships that are independent of the specific nature of the model of the system and surroundings. Now we are going to spend some time talking about boundaries. Boundaries define the nature of interactions or exchange between system and surroundings. Some of the commonly considered boundaries in thermodynamics are adiabatic boundaries, which allow for no exchange of thermal energy. This could be thought of therefore as perfectly insulated systems, a perfect insulation, an idealized version of heat insulation could be considered. This, of course, that doesn't necessarily result in an adiabatic boundary. There is an additional constraint that is imposed on an adiabatic boundary, which is that any kind of exchange, any kind of process that takes place within the system has to be reversible in nature, and we've not come to reversible versus irreversible. So I'm using this thing I'm sort of putting a little bit of a cart ahead of the horse, but we will see this in a little bit more detail in a few slides from now. Now again, another common boundary that is considered is rigid boundary, which means the boundary itself cannot move, it cannot displace, it is fixed in place. The third one is an impermeable boundary, which means no material can pass through it, and therefore this boundary will not allow for exchange of species between system and surroundings. Sometimes you also have some system called closed system, closed boundaries, which allows for no movement of overall mass. Then you are talking about impermeable boundary. This allows for no exchange of specific species, any individual species. These two seem to be very similar to each other. We will see why we have to sort of define these two separately. Versus, we have the opposite cases of adiabatic, which is diathermal, where there is free exchange of thermal energy allowed. This is again another idealization, right? Moving boundary, which allows for free movement of boundary. permeable boundary which allows for free exchange of specific species. So here we talk about this impermeable versus permeable. You can have boundaries that are semi-permeable, which basically means they allow for exchange of only a certain species, not all possible species. Open boundaries versus closed boundaries, which allows for free movement of overall mass. Now, adiabatic versus diathermal. This set of boundaries and the interactions arising from these boundaries between system and surroundings, the interactions are called heat interactions, which involve thermal energy. All the other interactions between systems and surroundings are called work interactions in thermodynamic parlance. So model thus, boundaries facilitate exchange of mass, individual species, energy between system and the surroundings. And thus, heat and work interactions cause either addition or removal of energy to or from the system. So now we are coming into the core of thermodynamics, which is basically thermodynamics deals with energy and its transformations and its exchange between systems and surroundings. So we have set the sort of one piece of the puzzle for the bigger analysis. So what is energy of a system? From our perspective, energy is a property of a system. Energy is stored in the system, and it is stored in two forms: potential energy, which is energy stored in the system by virtue of relative positions, and why relative we will see in a moment. Kinetic energy, which is energy stored in the system by virtue of relative motions, again why relative we will see in a moment. So potential energy is energy stored in the system by virtue of relative positions. Kinetic energy, energy stored in the system by virtue of relative motions. Now energy stored in the system is of two types: macroscopic energy, that is energy stored in the entire system in relation to other systems. So you are looking at an entire macroscopic entity, which is the system, in relation to another macroscopic entity. You are looking at what sort of energy is stored. And then the molecular or microscopic energy, energy stored in the entire system in relation to other constituents of the system like subsystems. We will describe what these two mean in some detail in the immediate next couple of slides. As I mentioned, in thermodynamics, microscopic is often used in the same context as molecular scale. So let's look at macroscopic energy. Macroscopic potential energy is gravitation, for example, gravitational potential energy, energy stored in a rigid body, solid, or a fluid by virtue of its relative position vis-a-vis Earth. So here is one macroscopic system. Here is another macroscopic system. By virtue of the relative position of this system vis-a-vis that system, you store energy in the system that you call as gravitational potential energy. So here there is this Earth, and there is, say, suppose there is a satellite, and that satellite is at a certain distance from Earth's center, and therefore vis-a-vis that Earth, the satellite has a gravitational potential energy stored in it, and this of course is undergoing a rotational motion which has to do with the kinetic energy. When you are talking about macroscopic kinetic energy, you are talking about kinetic energy of an entire body: rigid body translation, rigid body rotation, rigid body vibration. Again, you could have the fluid, entire fluid is translating, entire fluid is rotating, entire fluid is undergoing some sort of a vibration. All of this is possible. Where do you see entire fluid translation? Flow. Where do you see entire fluid rotation? When you have curved systems and you create rotations. And where do you see fluid vibrations? For example, when you have compressible fluids like gases, I am speaking, you are hearing. What is happening is that the air is undergoing a set of vibrations, compressions, and rarefactions, right? So all those macroscopic picture the energy stored, right, in a body, whether it is a rigid body or a fluid, by virtue of its relative motion vis-a-vis the surroundings. So this is one classic example: relative rotational motion vis-a-vis Earth, right? So there is a macroscopic kinetic energy, rotational kinetic energy for the satellite. Similarly, you have a relative translational motion vis-a-vis a stationary road. The road itself is not stationary because it is part of Earth, and Earth is undergoing some sort of a rotation, and it's going around the sun and whatnot. However, relative to the stationary road, okay, you have a car that is moving at a certain velocity, and there is a relative translational motion. There is a macroscopic kinetic energy of the car. Relative vibrational motion of the strings vis-a-vis the stationary guitar, right? So all of these are examples that you have encountered in daily life, in your school level and various other courses in college level, science courses. So these are familiar ideas. So this is macroscopic forms of energy. Now, the key thing to note here is that the coordinate frame of reference and the origin, if you look at the satellite as the system, the car as the system, the string as a system, the coordinate frame of reference and the origin lies outside the system. And that is why I mentioned across objects you are looking at some sort of interactions, and then you are looking at energy stored in your system by virtue of such interactions. Whereas molecular or internal energy, again, if you look at the molecular potential energy, again potential and kinetic energy, the molecular potential energy is the bond energy. It is either the primary bonds or secondary bonds. Energy stored in the molecules of a system by virtue of their relative positions with respect to each other. So you are looking at, say, a molecule like H2O, right? So the relative position between the hydrogen atoms, the oxygen atom, right, with respect to each other. And then you say that when they have come to a certain bond length, there is a covalent bond that is formed, and there is energy stored in that OH bond, and that is the primary covalent bond energy. And then you have the secondary bond energy, which is interaction between one hydrogen of one H2O and another oxygen of another H2O by virtue of the relative positions. So when they come close to each other to a certain distance with each other, there is energy that is stored by virtue of secondary or hydrogen bonding interactions. So this is molecular potential energy. You can, for example, in van der Waals secondary bonding, there are these potentials such as Lennard-Jones interaction potentials between two molecules in a system, and as the two molecules are far away in infinity from each other, then there is an attractive interaction, and then there is this green line that is seen here. This is the bond length of the induced dipole or some sort of dispersion interactions, as you might have studied secondary bonding Lennard-Jones interactions. And then this is the bond length, and if the two molecules are forced to be closer than the bond length, they will repel each other. In this area, there is a repulsive interaction. Now, what is molecular kinetic energy? Again, you are looking at molecular translation, molecular rotation, molecular vibration, kinetic energy that is stored in the molecules of the system by virtue of their relative motions with respect to each other. This is why we can talk about two molecules coming and colliding with each other, and then there is this sort of elastic conditions which you might have studied in kinetic theory of gases when you understood ideal gas systems, right? So this kind of kinetic energy is what we are talking about here. So you can have translation, rotation, vibration, there is bending, there is stretching, there is symmetric, asymmetric stretching. These are all the vibrational motions, and then those are the rotational motions, and then this is the translational motion in itself, right? So these are basically the different modes of energy stored in the system. Notice now that the coordinate frame of reference and origin lies within the system. So you have a system comprising a large number of molecules, and then you are looking at two molecules, all right? You say this is the position of one molecule, and where is the position of the other molecule relative to this molecule, you bring the second molecule from infinity closer and closer and closer, and here you form a bond, right? So in this system, the larger system is some system comprising so many molecules. Now here is your origin. So the origin is within the system, the coordinate frame of reference is within the system. Similarly, when you are looking at molecules moving, ideal gas molecules moving in a container, and then they are coming and colliding with respect to each other, each collision is described in terms of coordinate frame of reference and origin that is within the system, within the container itself, right? And this is the difference between the macroscopic potential kinetic energies and the molecular potential kinetic energies. The sum of these two is called the internal energy. So internal energy is the sum of all the potential and kinetic energies. Here the J's are all the modes available of interaction and kinetic potential modes, and energies of all the molecules, i.e. summation indicates the all the molecules that constitute the system, considering that there are, say, n molecules. Now let's try and, since we have this understanding of internal energy, let us try and understand what is the internal energy of a glass of water. We'll take our picture that we showed earlier, the macroscopic versus microscopic versus molecular. So a glass of water, say a quarter liter or 250 ml of water at ambient conditions, 300 Kelvin, 1 atmosphere. What is the internal energy? In order to do that, first let us estimate how many molecules, n molecules are there. So 250 ml of water is, I'm going to take the density to be 1 gram per ml or gram per cc, and therefore that's 250 grams of water dividing by the molecular weight of water. That gives 13.89 moles of water. That is roughly 8.365 into 10 power 24 molecules of water. Now, if I were to consider all the covalent bonding interactions and all the hydrogen bonding interactions and all the other dispersion interactions that exist between these many molecules of water, plus all the translational, rotational, vibrational modes of kinetic energies of individual molecules, and I start summing all of this, even if I set up the best of the best of the best high performance computing facility, and I wait for my lifetime and then probably all of yours put together, I'm not going to get an estimate of this energy. Therefore, it is impractical to consider molecular scale models for macroscopic systems simply because of the sheer number involved, unless absolutely essential, in which case you have to obviously reduce the number into some manageable quantity, or you have to construct simpler ways of going from this molecular picture to a macroscopic picture, right? And this is a fundamental problem in thermodynamics. Again and again and again we keep revisiting this kind of a problem in thermodynamics in different contexts. So how to go from molecular to macroscopic models? Now we will come back to that problem in a while. We still need to put in place a lot of basic pieces. So let's start with what is called state of a thermodynamic system. And here is a hypothesis to start the whole thing. The state of a thermodynamic system is defined by its internal energy. So I declare that this is the state of a glass of water, defined by its internal energy. Internal energy, as we saw just now, is a property with molecular origins, and it can be defined in molecular scales, but it can also be defined in microscopic and macroscopic scales. We better do this, otherwise we just aren't going anywhere. We are, for your lifetimes and my lifetime, we will still be sitting and computing the internal energy of a glass of water. So of course we can define internal energy in molecular, microscopic or macroscopic scales, but nonetheless you understand that the origins of this internal energy is molecular in nature. So according to the scale, whether it is molecular scale, microscopic scale, macroscopic scale, the number of independent variables needed to specify or define the internal energy of the system will vary. We saw just now that if we were to define the internal energy of a system from molecular perspective and you had a macroscopic amount of the substance, then the number of independent variables needed would be enormous. Some 8.365 to 10 power 24 molecules. For each of this, you need positions, you need momenta and whatnot. So there's a lot of variables needed. But depending on the other scale, the macroscopic scale, the number of independent variables needed to specify the internal energy of the system will be far less. It has to be far less. What that will be, we will see in a moment. So as we were mentioning just now, the molecular state of a thermodynamic system is defined by the positions and momenta of each molecule that is part of the system. 3 times as many momenta as the degrees of freedom of motion. So if there is only a translational degree of freedom of motion, so and then you have x, y, z, or r theta z or r theta phi, depending on what coordinate system you are looking at. So 3 times as many momenta, and then if you have translational plus rotational, then again for rotational you will have 3 times as many as well, and for vibration and so on, right? So u is defined as u of a function of ri, where I is the number of index indicating the number of molecules, and pij for each molecule for how many ever degrees of freedom there are. So you have to define that kind of momenta. The macroscopic state of a thermodynamic system. Now let us start addressing how to go from molecular to macroscopic, and first we define the macroscopic, then we will see in subsequent lectures how to go from a molecular to macroscopic picture. The macroscopic state of a thermodynamic system, on the other hand, is defined using the thermodynamic framework of interactions between system and surroundings. This is why we sort of put this thing in place, and therefore in the macroscopic state of thermodynamic system, my internal energy is going to be defined by the nature of the boundaries that are involved. So now we sort of present what is called a state postulate. It's often termed a state postulate. The number of independent variables needed to uniquely specify or define the macroscopic thermodynamic state of a system is equal to the number of work interactions available which come from the boundaries. Remember, this heat interactions, work interactions, right? The number of modes of work interactions, we looked at 2 modes at least. One is a moving boundary mode and the other was exchange of species mode, right? So similarly, how many ever number of modes of work interactions available plus 1, this 1 is for heat interactions, and at least one of these variables, right, the number of independent variables, at least one of which should be an extensive variable, which we have not defined what it is so far. We will define one of these subsequent slides. So plus 1, as I said, is for heat interaction, irrespective of whether the boundary is there, thermal or adiabatic. And why this should be the case is something that we will see in one of the subsequent lectures. Now, so in other words, whether there is, even if you have a perfectly insulated no thermal energy exchange, that mode is always needed. And why that would be the case? For those of you who have earlier studied thermodynamics and laws of thermodynamics, this idea is contained in the second law of thermodynamics. But we will see. Now, work and heat interactions that we've been talking about, they'll be defined shortly. Extensive properties also will be defined shortly. So I'm specifying 3 variables here. What these are, we will see. Again, all of these will be defined in subsequent lectures, and partly in this lecture too. But 3 variables, 1 for heat and 2 for the 2 work modes. S is a property called entropy. V is the volume of the system. N is a measure of the number of molecules in the system. It could be either seen as a number of moles or mass. Entropy, like internal energy, is a property with molecular origins and can be defined in molecular and microscopic scales. There will be an entire lecture that will be dedicated for what entropy is. So for the time being, I just request all of you to please accept the fact for the time being, just take it for granted that there exists a property called entropy. And there exists these work interactions, heat interactions, and there exist extensive intensive properties and so on and so forth. We'll define one by one as we go on. Some system properties such as internal energy, entropy, volume, and number of moles of a substance present in the system are called extensive properties. What are these extensive properties? Extensive property, say V, in this case volume of a system, is the sum of the properties of its component subsystems. So if I were to take a system and break it into two, break each of the two subsystems into two, and then so on, so forth, then if I take my extensive property, I look at all the constituent subsystems measure of that property, say volume. If I add all the volumes of all the subsystems, I will get the total volume of the system. Same will be the case with respect to number of moles. So if I have total 100 moles and I have partitioned it into, say, 2 moles in one subsystem, 5 moles in one subsystem, 10 moles in one subsystem, 18 moles in one subsystem, and so on, so forth, and I add all the number of moles of all those subsystems, totally I will get 100 moles, and that is this idea behind the extensive property. For example, a volume of glass of water is the sum of volumes of 2 half glasses of water, right? This is the idea. Alternatively, there are other system properties such as temperature, pressure, and I'm introducing a term now which is again new, called chemical potential, which we will be discussing in a separate lecture, an entire lecture dedicated to chemical potential. Okay, these are intensive properties which are independent of the size of the system. Temperature of a glass of water, for example, is not the sum of temperatures of 2 half glasses of water. In fact, what is this temperature of the glass of water? If I took 2 half glasses of water, they are all at the same temperature, suppose, and I just mix the two. Again, the total glass of water will also be at the same temperature. In other words, all 3 temperatures will be the same. It's independent of the size of the system. Now, to recap, what did we say in state postulate? We said that at least one of the independent variables needed to specify the state of the system must be extensive. That's sort of common sense if you think about it, because you need to capture the size scale of the system. So if you have all intensive properties, you will never be able to capture the size of the system. So you don't know whether the system is one small collection of, say, a few molecules, or it is a collection of millions and billions of molecules, or what, you will never know. So you have to have at least one of the variables which has to be extensive in nature in the number of independent variables that you choose to specify the state, macroscopic state of a thermodynamic system. One of them should be extensive, and each variable should correspond to one work mode of interaction or the heat interaction +1. So this is the way, this is the postulate that sort of says how to define the state of a thermodynamic, macroscopic state of a thermodynamic system. Now then, we have to having some idea of how to define states of systems. Now we are looking at what sort of interactions take place between systems, system and surroundings, and so on. And these interactions are defined by processes. Processes are how systems interact with each other or with surroundings, and therefore processes end up changing the state of systems. How are processes defined? processes result in exchange of mass or species or energy, etc. All these change the internal energy of the system. State of the system is defined by internal energy of the system. So if this state is changed, internal energy is changed, and vice versa. How are all this happening? They are happening through interactions, and these interactions occur via boundaries, which is why we had to spend the sort of time defining those boundaries, which essentially meant we define the nature of processes that will take place. So adiabatic, thermal, rigid, moving, permeable, impermeable boundaries. Okay. For each process there exist bulk transport mechanisms or exchange mechanisms, molecular exchange mechanisms. The rates of these processes, fluxes of these processes are modeled using constitutive relations. Now we start coming, trying to establish connections between the continuum transport systems and this, except there is still one big elephant in the room, which is the whole reversible versus irreversible thing, which we will come to that. The set of all the states of the system. So I start from one state, and through a process, the system state keeps changing. It reaches another state. Okay, so there are so many intermediate states that the system would go through, isn't it? So if I compile all that set of all that states into a single set, essentially during an interaction or a process, I call that as the path of the process. Okay, so the path of the process is defined by one initial state, one final state, and a whole set of intermediate states. So when I'm talking about this path this process resulting in changing in the energy, and therefore the energy is exchanged, a stored energy in the system is exchanged with the surroundings. Okay, so I have to consider the internal energy which is stored in the system, and then the energy that is exchanged with the surroundings. Right? The energy exchange happens by way of interactions through boundaries. This is called processes. These result in energy in transit, that is energy that is exchanged. Generally, two types of energies in transit have been observed over centuries. One is heat, one is work. Okay, so this is why these heat and work interactions were identified. So this is from a very historical perspective of how these interactions have been observed. If any of you is interested in history of science, fascinating accounts are available in the literature as to how thermodynamics evolved as a subject, right? And there's a lot of these discussions center around heat and work, and how the understanding of heat and work has continued to evolve over a period of time. So for each mechanism of interaction between system and surrounding, except that of thermal energy, which is defined as heat, right? So for each other non-thermal energy, it's sort of non-heat interaction between system and surroundings, a work is defined. For example, you have a moving boundary of a system that is displaced outward due to excess internal pressure. This is a simple logical thing. So there is a boundary which can be moved. Okay, so on the one side of the boundary there is a pressure that is applied, on the other side of the boundary there is a pressure that is applied, and both pressures are equal, the boundary won't move. If the internal pressure is more, then the boundary will displace outward. If the external pressure is more, the boundary will displace inwards, right? So here we have a moving boundary of a system which is displaced outwards due to excess internal pressure. And this causes naturally the system to expand. The work done is given by integral PdV, the rate at which the system volume is expanding, and what is the pressure that is causing this push, right? So this is your work done. The rate at which work done is defined by the rate at which the volume is expanding. So that is the rate of work done. Now another example: a system has open boundaries through which bulk fluid enters and leaves. It's just fluid flows. Fluid flows through the system driven by higher pressure outside one of the open boundaries and lower pressure on the outside of the other open boundary. So there is fluid flowing through. The work done is integral VdP. Now this is a this is our your classic control volume analysis and Eulerian perspective, right? So you look at a fixed volume, there is stuff coming in, stuff going out, right? So on the one side of the dashed boundary that you typically draw for the control volume, right? There is higher pressure on the other side of the other boundary, dashed boundary that you draw. There is a lower pressure, and then flow is happening from the region of higher pressure to lower pressure. So the work done in displacing that fluid is integral VdP, where V is the control volume, dP is the change in pressure, and then the rate at which this work is done is integral V, rate at which the pressure changes. Now, the system has permeable boundaries through which one of the species I in the system is selectively transported to the surroundings. Now this is like having a membrane, and you have in your water filters at home you have you pour your water, and then there is a filtration that takes place. All the pollutants and all the suspended solids, dissolved solids are all, the filter is an ideal filter. They are all retained in one side, and then H2O alone is selectively transported through the membrane to the outer region where you collect the treated water. So this exchange is driven by chemical potential, which again, as I said, will be discussed in a separate lecture. Higher chemical potential in the system than in the surroundings. So the work done is, so this mu I integral mu I dNi, right, where Ni is the change in the number of moles due to this transport. And now if you look at the rate at which this work is done, then integral mu I dNi dot is the rate at which Ni is changing with time. Ni denotes the number of moles of species I. Chemical potential will be defined in a future lecture. So your V, dP dot, mu I, dNi dot, all of these come from constitutive models. We'll see one such constitutive model. Now, energy in transit, heat is thermal energy or molecular kinetic energy in transit. Why do we need a distinct type called heat will be discussed in a future lecture. If it is not, then it has to do with second law of thermodynamics. That's just mentioned up there. It's discussed in thermodynamics courses. Constitutive laws for rates, fluxes of heat transfer, conduction. You have Fourier's law, convection. Convection within a species. You have, this is your mass flux times CV, which is heat capacity at constant volume, and then delta T, which is basically the difference in temperature, and CV can be typically modeled using some empirical relationship. Radiation, Stefan-Boltzmann law. We know that the thermal energy stored in the system is stored as molecular, translational, vibrational, rotational, kinetic energy. How does addition or removal of heat cause changes in the molecular thermal energy? This is discussed in a subsequent lecture on entropy. So this whole idea of why you need a distinct type of heat, this is all discussed in a subsequent lecture on entropy. Now we come to a central idea in thermodynamics, which is the concept of equilibrium. Right. An equilibrium state of a thermodynamic system is a type of end state or rest state or a stationary state of a system. Example, after a process is completed, where no further change in the state occurs unless disturbed by an external driving force, which means another process starts. So, an equilibrium state is a rest state of a system where no further change in state occurs spontaneously. If two or more subsystems are in equilibrium, then you say that there is no net flow of either matter or energy between the systems. Though through the modes of interactions that are available between the system, which of course dependent on the nature of the boundaries separating the systems. In other words, both systems have come to a joint rest state. For such interaction between the systems, for each such interaction, modes of interaction between the system, there is a driving force. The interaction proceeds at a certain rate, and eventually the system reaches the rest state. So the systems jointly reach the rest state. So for example, there could be simultaneous exchange of heat and displacement of a boundary, which is what happens in for example, an engine. You have a piston and a cylinder, and there is this sudden combustion of fuel, which causes a large generation of heat, along with which basically pushes the piston outward. So there is a stroke of the engine, right? So basically this means simultaneously there is a mechanical work done, as well as energy, heat that is released, right? Both take place simultaneously, for each of which there is a driving force, and each proceeds at a certain rate. And if the system is allowed to reach the rest state, then jointly through both modes of interaction, the system and the surroundings will, the piston cylinder system and the surroundings to which the piston gets displaced and the energy heat gets released, they both will eventually together come to a joint rest state when there is no further driving force available and there is no further net flow of matter or energy between the systems. Then there is basically, you have a joint rest state that is reached. Now finally, very important idea of reversible versus irreversible processes. A reversible process is one whose direction can be reversed to bring a system, and importantly not just the system but its surroundings as well, back to the earlier states. So you go through a path, you can exactly retrace the path, and you can bring the system and the surroundings back to the original state by infinitesimal changes to the state of the system. And in fact, you don't have to necessarily only retrace the path. You can go through a different set of paths and come back to the initial starting state of both the system and the surroundings, and the properties of the system and the surroundings will be the same. So the original what it was when you started the whole process, right? So you could go through cycles, for example. This is something that is very commonly studied in thermodynamics, where you can have an idealized reversible set of paths which constitute a cycle. So you start from one state, you go to another state, and come back to the same original state. And so when you have come back to the original state, then the temperature, pressure, entropy, energy, right, chemical potential, all those parameters, properties that we mentioned without formally defining all of them. Some of them we have defined, but many of them we have not, right? All those values are back to the same values for not only the system but the surroundings as well. So, and therefore this, in order to effect this reversibility, typically what is stated is that the changes to the state of the system is done in an infinitesimal manner. Such a reversible process ends in an end state or rest state of equilibrium. The subsystems reach a state where there is no net transfer of species energy, displacement of boundaries and so on and so forth. An irreversible process, on the other hand, is one that results in new states from which the system and surroundings cannot be restored back to their earlier states by infinitesimal changes to the state of the system. So I can construct a cycle with irreversible processes, and I can bring back my system to the same temperature, pressure, or whatever it started out with. But if I brought the system to that particular initial state, the surroundings will not be at the same initial state. There would have been some irreversible permanent change that will have happened. The surroundings will be at a new state. Alright. And therefore, you cannot bring the system and the surroundings, restore them back to their earlier states by inflexible changes in an irreversible process. So such an irreversible process typically ends in a rest state of completion. Subsystems reach a state where irreversible exchange energy transport is complete. Now, you, for example, you have an irreversible reaction into a new state, completely new state, right? So you have an irreversible reaction. You take, for example, hydrochloric acid and sodium hydroxide, and you mix them together. You do the titration. You have formed sodium chloride and water, and that's an irreversible end state. You cannot retrieve back HCl and NaOH through changing the process. So when you have reversible processes, the driving forces are conservative. In other words, these forces result in energy exchange, this exchange that takes place, energy in transit that takes place. So what I'm talking about here is both work and heat, okay, that is independent of the path of the process, but only dependent on the end states of the system, because they can always come back to the original state of the system. So it doesn't matter whether I go from here to here and I'm back, or here to here and I'm back, here to here and I'm back, looking at the cursor or the laser pointer. So it doesn't matter so long as I'm doing this in a reversible manner. All right. So once I come back to the same state, I reach, both the system and the surroundings have reached the same initial state, right? And therefore, the energy exchange, which is basically the work interactions and heat interactions, if I look at how much energy has been exchanged as work or heat, that will be finally independent of the path of the process, but it will only be dependent on the end or equilibrium states, the rest states of the system, initial final states of the system. If the system, as I said, reaches the same end state as its beginning state, then there is no net work done, because I have come back to where I started, since there is no net change in the energy of the system. For such a process, the driving force can be expressed as the gradient of the energy, called the potential. Don't confuse this with potential energy. So, on the other hand, if I have an irreversible process, at least some of the driving forces are non-conservative. In other words, dissipative. These forces result in energy exchange that is path dependent. Classic example is friction. You take two palms of your hands and you rub them. You can hear the rubbing and there is heat generated, right? And it depends on how I rub it, right? The hand motion that I create will result in the different types of energy exchange, and I cannot get that energy back. I cannot get my system as well as the surrounding back to the original state, right? So this entire process becomes path dependent. So now we are trying to answer this question that we posed at the beginning of the setting of the thermodynamic framework. You want to go from molecular to macroscopic quantities. Consider a macroscopic state of a thermodynamic system. Internal energy, as I said, is then a macroscopic property with molecular origins. This means many molecular arrangements can result in the same macroscopic internal energy. We will see this in some substantial detail in the lecture on entropy, ranging from, for example, an extreme situation of all potential energy and no kinetic energy. So that suppose I have a glass of water, and the glass of water has some internal energy of 100 joules. Alright, and that 100 joules could come from all potential energy and no kinetic energy of any kind, which is basically where all the molecules are frozen, 0 Kelvin, right? To another extreme of all kinetic energy and no potential energy, where I have, say, for example, an ideal gas, all my water molecules are all in vapor state, for example, right? So the question that comes is, at equilibrium, which macroscopic state is the most likely state? Which arrangements will be the most likely arrangements? this is a fundamental question, and this question is going to get addressed 2 lectures from now. So with that, we come to the end of this long introduction, foundations to fundamentals of thermodynamics. This, as I said, is a detour. I request all of you to sort of patiently walk with me through this process. We will come to a certain end state where we not only gain a good, hopefully a good understanding of the thermodynamics and the sort of framework in place available to describe energy of a system, modeling energies of systems, and modeling the interactions between systems and surroundings which result in energy exchanges, and the various properties that are associated with this sort of energy exchange, and how do we go towards writing conservations of energy. So thank you for your time and attention. I hope you are able to follow what has been discussed in this lecture. Largely it is very introductory and probably very familiar, and yet there are certain pieces in place that are probably a little bit new for an undergraduate, fresh undergraduate student. So if you have to re-listen to this lecture a few times, please feel free to do so. And as always, I am available for any interactions and questions and clarifications that you may have. You may contact me either through the YouTube channel or through personal contact information. Thank you once again. Have a wonderful, wonderful day.